Welcome to the Unit 9 and the video series that will be on momentum. This video series will be composed of 3 videos that will cover the introduction to momentum, some momentum problems, and collisions. Let's go ahead and begin. Before we talk about momentum, it's important to talk about what is the definition of momentum. Now, momentum can be defined in 2 ways. Both are the same, but just different ways of saying the same thing. The first way that momentum can be defined as mass in motion. So if something has mass and it's moving, it has momentum. Another way momentum has been defined as it is the measure of how hard it is to stop something. So if you have an object that is moving and it has a lot of momentum, it is very hard to stop. However, if you have an object that has very low momentum, it is very easy to stop, or at least easier. Now we can quantify momentum by coming up with an equation that looks like this. Now in this equation, notice what the variable for momentum is. Kind of interesting. Momentum does not have the variable m, but actually it has the letter p. P stands for momentum. So when you see that, notice that that's talking about momentum. Now how you can calculate momentum is very simple. Mass times velocity. And remember, mass has to be in kilograms, and velocity has to be in meters per second. Now when you calculate momentum, your units are going to simply be kilograms meters per second. There is no simple unit for momentum, and so from here on out, when we calculate momentum, those will be the units: kilograms meters per second. Okay, so let's do some very simple problems to get the idea behind. The question here says a car possesses 20,000 units of momentum, units being the kilogram meters per second. What would be the car's new momentum if, and then there's 4 changes. So remember, momentum is mass times velocity. Now, the normal original momentum is 20,000 units, and we're asked to figure out what would be the car's new momentum if the following changes were changed. So for example, letter A, if its velocity was doubled. So in this case, we have momentum equals m times 2v. Since there's a direct relationship between momentum and velocity, if you double the velocity, you will double the momentum. And therefore, the velocity would be, the momentum would be 40,000 units of momentum. Letter B says, what if its velocity was tripled? Well, same reasoning applies. Momentum is mass times velocity. And since velocity is tripled, your momentum will also be tripled. And so 20,000 tripled ends up being 60,000 units of momentum. Letter C has the mass being doubled. And this usually comes by adding more passengers or a greater load or something like that. But the idea is that the mass of the car has been doubled. Okay, well, momentum is mass times velocity. This time, the mass is being doubled, whereas the velocity is staying the same. But mass also has a direct relationship between momentum and mass. And so if you double the mass, you will double the momentum. And therefore, it'll be 40,000 units of momentum. Finally, letter D says both its velocity was doubled and its mass was doubled. So that would be double the mass and double the velocity, or in other words, it'll be 4 times the amount of momentum, because 2 times 2 is 4. And therefore, 4 times 20 ends up giving you 80,000 units of momentum. So now we have seen not only how can we calculate momentum, but we can also see how changing mass and changing velocity affects the momentum. Let's look at another example. In this picture, we have a situation where you have a halfback, a tight end, and a lineman. The halfback is 60 kilograms, the tight end is 90 kilograms, and the lineman is 120 kilograms, and they're running down the football field. Now you'll notice in the picture, it gives you a ticker mark diagram of what's going on here. We've also called these motion maps. But the idea is that for every unit of time, a mark has been made with a dot. So you can see every dot represents a unit of time. And let's say it's a second. So every second that goes by, a dot is being taken. So from the visual picture, which football player is the fastest? The lineman, the tight end, or the halfback? The answer would be the halfback. The halfback is the fastest, and that's because he goes a further distance in a unit of time. For example, after 1 second, the halfback was able to get from here to here. However, after 1 second, the tight end was only able to get this far, and the lineman even shorter still. So it looks like the halfback is moving the fastest simply because he goes further in the same unit of time. Now, let's fill in what those missing velocities are. We know the lineman is 3 meters per second, but we need to figure out what is the velocity of the tight end and what is the velocity of the halfback. There are several different ways you can do this. I'm going to attempt to explain it in one way. Notice that if the lineman is moving 3 meters per second, the tight end we know is moving faster. And notice the ticker marks. The tight end was able to get the same distance that the lineman was able to get in half the time. For example, it took 2 seconds for the lineman to get from here to here, but it only took the tight end 1 second. So what does that tell you? Well, that tells you the tight end is moving twice as fast. And so if the lineman is moving 3 meters per second, the tight end must be moving 6 meters per second. We can do the same thing for the halfback. The halfback was able to get 3 times as far as the lineman in only 1 second. So we can say that the halfback is moving 3 times as fast as the lineman, and therefore the lineman is moving 9 meters per second. Once again, because he was able to go 3 times as far in the same amount of time. I'm going to erase these marks so you can visualize that. Maybe it's a good idea to pause the video and take a moment to kind of conceptualize that for yourself before we move on. Okay, so now that we have the velocities of each, the first question's already been asked. What is the velocity of the tight end and the halfback? We figured that out. And now the second question is, who has the greatest momentum? Remember, momentum is a product of mass times velocity. So we have the lineman, and the lineman is, we are told, is 120 kilograms. So for the lineman, his momentum is going to be 120 kilograms times his velocity, and the velocity for the lineman is 3 meters per second. If we multiply those out, we end up getting a momentum of 360, and remember the units are kilograms meters per second. Next, let's do the tight end. The tight end, if we go back up, has a mass of 90 kilograms, and we figured out that the tight end is moving 6 meters per second. If we multiply those together, we end up getting 540 kilograms meters per second. Finally, we have the halfback. And the halfback is the lightest. If we go back up, the halfback has a mass of 60 kilograms. So 60 kilograms times the halfback speed, which is 9 meters per second, we end up getting 540 as well. So you can see that the halfback and the tight end actually have the exact same amount of momentum. A lot of times, people think that the most heavy object, in this case the lineman, would have the most momentum. But that's not true. It's a product, like I said, of velocity versus mass. Now we're going to look at what would happen if we changed momentum. Okay, what would have to happen if we wanted to change an object's momentum? Well, remember, an object's momentum is a product of mass times velocity. If you wanted to change the momentum of the object, you would have to change one of those variables. So either the mass would have to change, or the velocity would have to change. Now, it is possible for the mass to change. For example, if you had a car and it was going a certain speed, and then you added more people into that car and went the same speed, you would end up having a greater momentum simply because the mass is larger. However, when we're looking at physics problems, most of the time, we're not going to be looking at mass changing, but instead, we're going to be looking at velocity changing. We're going to be looking at an object that is either speeding up or slowing down. And therefore, if we wanted to change momentum, most of the time, it'll be because there is a change in velocity. So we can calculate change in momentum by taking the mass times the change in velocity. Now, let's revisit Newton's second law because we're going to see that that actually helps us out when we're looking at momentum. If you remember, Newton's second law is force equals mass times acceleration. Now, I'm going to rewrite that into something that we can see a little bit differently. So force equals mass, but I'm going to rewrite acceleration into its equation form. And if you remember, acceleration is simply change in velocity over change in time. Now I can rearrange this equation by timesing both sides by delta t. If I do that, the delta t's cancel out, and I end up getting force times delta t is equal to mass times delta v. Now, we already know what this side equals. This side equals the change in momentum. But if we look at the other side, the left side, we have another product here, force times change in time. What is that? Well, force times change in time actually has a name. It's called impulse. So we end up getting what's called the impulse momentum theorem. And what that states is the force times the change in time, there should be a little delta there, force times change in time, which is your impulse, is actually equal to your mass times change in velocity, which is our change in momentum. Notice impulse actually has a variable. The variable for impulse is j. Now that seems kind of weird, almost as weird as momentum being p. The reason why impulse is not the letter I is because later on we're going to learn that I actually stands for current in electricity. So the abbreviation or variable for impulse is j. Now, what does the impulse momentum theorem actually state in words? What it states is the following. When an object collides with something, it experiences a force for a certain amount of time. This is known as your impulse, a force acting on an object for a certain amount of time. This impulse is not only the cause of the change in momentum, but it's equal to the change in momentum. Now we're going to be doing a lot of example problems with the impulse momentum theorem, but let me give you one example that will help you kind of visualize what's going on here. If you think about a baseball fields, the outfield are outlined with a certain amount of padding. And we'll talk about why that is later on, but there's a certain amount of padding. And you think about a baseball player that's running to catch a fly ball, and when they catch it, they run into the padded wall. Now, when that happens, there is a certain force that the wall exerts on the baseball player, and it happens for a certain amount of time because the baseball player doesn't become permanently stuck to the wall. They come in contact with the wall briefly until they bounce back off and continue on with the game. If we were to take this force that's acting on the baseball player multiplied by the amount of time that the baseball player is in contact with the wall, not only is that what's causing the baseball player's change in momentum, because if you run into a wall, you slow down a bit, but it's also mathematically equal to the change in momentum. We will look at this and some math problems in the next video.